Hi everyone, this is Kevin from PCI Geomatics. I'm here with Jason. We're just getting ready, final preparations for today's webinar. Just stand by. We're going to let a couple of minutes go by, let people settle into the webinar session, and we'll be right back. All right, well, it's 2 o'clock on the button, and we're going to get started with today's webinar. Well, first of all, welcome to everyone to our webinar. We will be talking today about UAV processing and information extraction with Geomatica. Okay, just hang on. I just need to set up a few things here. Perfect. Okay, so today's presenters are myself on the left. We're actually reversed, I guess. I don't know how the cameras are set up, but Jason's on the left live and I'm on the right live, but in the pictures we're reversed. So I'm the Director of Marketing here at PCI Geomatics, and Jason is one of our technical solution specialists here at PCI as well. And we're really happy to be here with you. So the first order of the day is just in terms of logistics. So the lines are muted. You can carry on, have conversations if you're with other people in the room. You won't be disrupting anything. You can ask questions throughout the session. There's a questions panel that should be available in the interface. And you can also raise your hand. We also have myself and Jason sort of watching the questions. So we'll try to answer them as we're going. We also have Mauro, who's here in the session with us, and he's available if something comes up, you want to raise your hand, or if you have a specific question, he'll try to help you out as well. So this webinar is actually the third webinar in a series of 4 webinars, which we are doing over the course of about a month or so. The key event, I guess, that initiated this series of webinars is the latest release of the Geomatica software platform. And that was on November 26th. We presented an overview of the Geomatica platform, Geomatica Banff, which is our latest release, on November 26th. And since then, we have rolled out the specific topics that address key technology that's been released as part of the release. So last week on Tuesday, on the same day, we presented Object Analyst, Image Classification, and Automation in Geomatica, and also using Python, and there's some resources available for that. You can go back and watch the webinar in case you missed it. Today we're doing UAV processing, and this week on Thursday we're doing another webinar which is going to be Sentinel-1 tops. So be sure to check those out if you missed any, or register for the ones that are coming up, the last one that's coming up on the 12th. So just a few quick words about our platform. So we like to describe our technology as being a platform that enables the development of tools and processing of imagery. And really, it gives you the scalability and flexibility to work in different ways. So on the left, we have our image analysis tool, which is called Geomatica. It has a series of tools that are part of it that allow you to view imagery, process imagery, produce information products such as extract digital elevation models, make ortho images, or if you're doing any kind of advanced remote sensing application, we have a lot of tools for doing object-based and change detection. There's just a really rich set of tools. We've been around for 37 years, PCI has, so we've been developing this technology and it's all available as individual algorithms. And those algorithms can be put together into workflows using our Python API, which will allow you to automate workflows within Geomatica tools. Or if you're looking at higher volume production, then you can leverage our GXL system, which is a tailor-made system for processing large amounts of data for specific workflows. So we have specific workflows that we've been working on lately for creating analysis-ready data. And we also have a very successful set of tools for doing large volume production as it relates to orthoing and mosaicing large land masses, such as countries or continents or cities and what have you. So it's a platform, it's flexible, it's scalable. You can work within the GUI environment, you can deploy it on the cloud, you can work within the enterprise. It's all possible. Just a quick word on our software release. So as I mentioned, November 26th was the official release date of Geomatica Banff, which is the latest version of our Geomatica software. And you can see the green flags all across the top there are the major releases that have been coming out since 2012, so over the last 7 years. And the red flags are the service packs, which include typically known issues like bugs that we fix, but also new features that we add in. And we'll be talking about a couple of those features that are only available in certain environments today, but are going to be rolled out as part of service packs. So if you're a customer and you've maintained your license and paid for updates, we hope that you see that you're getting value as we continue to improve the software, add new features, and fix bugs along the way. So before we get into the actual subject matter, I do want to launch a quick poll to get a sense from the audience what it is. So today's topic is UAV processing. So we'd like to know what you're using currently. There's no right or wrong answer. It's basically we just want to know what it is that you're currently using. So maybe for UAV processing, you're using Pix4D, maybe you're using Agisoft Photoscan or Metashape, I believe as it's known now. Maybe you're using Trimble US Master, Drone Deploy, or maybe you're using something else which we don't have listed here. There's a lot of different options for UAV processing, and we'd love to hear what you're using, and hopefully we can show you what we're capable of, and you can consider that in the future. So if you did pick other, we'd love to hear what that is. So I'm going to leave that open for just a few more seconds and show you the results. So I'll just quickly share that for everyone's benefit. You can see that Pix4D and Agisoft are definitely used quite a bit for UAV processing, and we've got some quite a few other people doing other things which we'd love to hear about. So that's awesome. Thanks for that input, and hopefully that's helpful. So back to our webinar. So what we want to talk about today is some new capability that we've released as part of Geomatica Banff. So Geomatica Banff is our code name for our software. The trademark is Geomatica, but we've chosen to highlight some of the beautiful areas within Canada. We are a proudly Canadian company, and so the theme, I guess, or the code name for this release is Banff, which is a national park in Western Canada and Alberta. Today's webinar is going to address the following topics. So we have scheduled a full end-to-end demonstration of the UAV processing workflow within Geomatica. Jason's going to be giving you that demonstration. We hope that we can show you, we'll also plan on showing you how to leverage our powerful and unique live editing tools, and I'll describe what those are, and then Jason's actually going to show you with some real data. We'll talk about some of the best practices around deriving one-to-one ground sample distance or GSD digital surface models. And then we're going to switch gears a little bit and do a second set of slides, short slides. And I'm really mainly going to emphasize Jason's demonstration on using UAV imagery to extract information within the Geomatica platform. we're going to showcase our object-based image analysis tool that could be quite useful for automatically extracting features from UAV imagery. We're going to focus on a specific demonstration where we were able to extract solar panels from UAV imagery collected in a village close to Zurich by a drone known as Wingtra, which is from Switzerland. So some of the key highlights for this new release and why we think it's relevant for UAV. So we have done quite a bit of testing internally. We purposefully downloaded a lot of the sample data sets that are available from eBee, from Wingtra, from some DJI. We have a lot of customers who've been asking us over the years whether we support UAV data, so we have a lot of different UAV platform data available for testing. And we did quite a bit of testing, and this is just kind of a quick summary. It's not all of the cameras. It's by no means an exhaustive list, but it's just to give you a sense of the different elements of UAV support, if you will. So typically you have a platform, which is either a fixed wing or a VTOL drone. And as you can see, we actually have the three different versions there. So we have fixed wing, which is eBee, Wingtra, which is a vertical takeoff and landing, and then DJI, which is a quadcopter. And we've also worked with custom UAVs. And those platforms, depending on what you're working with, are either you're using the custom camera that ships with that drone, or you're using another camera. So that's just a list of some of the cameras that we've seen on some of those drones. And then in terms of channels, you know, we've seen a lot of data that simply collects RGB data, but we have seen some images collected with RGB plus NIR, and we've also seen some thermal data. So essentially our technology should work with all of these different platforms. We've performed a lot of testing with a lot of these different data sets. So there's a lot of support for a lot of different UAV platforms. And one of the nice things about, I think, where we sit in the market today with our UAV package is we're benefiting from all of the work that PCI Geomatics has invested in supporting aerial data processing. So about 6 years ago, we, PCI, invested heavily in the development of technology to improve our ability to handle digital frame cameras. And when I say digital frame cameras, I mean more traditional, I guess, digital frame cameras. We're talking about the big systems like the UltraCams, the RCD30, the ADS cameras, like all of those well-calibrated professional grade systems that are out there collecting data. And so what we did is we implemented support for those. And what that meant is we had to be able to extract elevation models at a very, very high level of precision. So the DSMs that we're extracting are done through the implementation of an algorithm known as semi-global matching, or SGM. And that's the algorithm that really allows us to leverage the full capability of aerial cameras, such as the traditional digital frame cameras, as well as the UAVs now with the UAV data sets being collected. So we have the ability to generate those DSMs at 1-to-1 resolution. We have the ability to filter those automatically to generate a digital terrain model. Then you either have the choice as a user to create a DTM ortho image or a DSM ortho image. And if you have building models, you can also do a true ortho image. But our DSMs, because they're at 1-to-1 resolution, you can actually use those directly to create a DSM ortho image, which is similar to a true ortho image, if you will. And then of course we have all the ortho mosaicing, and we have some other tools that are part of our aerial package, which we think you're really going to find useful for UAV processing. This is kind of the traditional workflow with a more professional grade camera like an UltraCam. So normally what we do is we ingest TIFF images that either have 3 channels or 4 channels in the case of near infrared. Then we import the exterior orientation and the camera calibration file. And then we either use an externally derived DEM or we derive the DEM ourselves using our software. Either way, once you get to the point where you're about to generate the orthos, one of the things that a lot of people struggle with in the aerial market is the ability to preview what the ortho is going to look like before they generate it. So there's a kind of a lengthy cycle where you make edits to the DM, you regenerate the ortho, you inspect the ortho. If you're still not happy, you go and you make that edit again. So we have a tool or a series of tools that we call Live Ortho. And what you're seeing on the screen is basically two different ortho images that are being flickered back and forth, and it's meant to be used as a quality assurance tool to ensure that the ground is not moving. If the ground is moving, it's because there's a problem with the DM, which you can interactively fix live inside our software and then see the result. The next step is the color balancing. So typically when people are doing color balancing, what they're doing is they're automatically generating seam lines, and then if the seam lines are in the wrong place, or if the color balancing along those seam lines is incorrect, you have to edit those seam lines and regenerate the mosaic. And so what we have is a tool that actually allows you to interactively drop what we call dodging points, either along the seam line, we call those edge dodging points, or inside an area on either side of the image where you're trying to adjust the colors or the brightness or the contrast. Those are called floating dodging points. So our color balancing tools are quite advanced and very flexible and will allow you to achieve really that high level of quality with UAV processing, as well as other data like satellite or aerial, traditional aerial. And then we have another tool, a set of tools. We call it Smart Geofill, and over here what you see is Smart Geofill being used on the right to bring back some of the contrast over an overexposed building rooftop. So you can see that we sample a large area around the building, and then we ask for the exposure to be corrected on the top of the building just to bring back some of the contrast. So all of these tools that we've developed for aerial data are there and they're available for you to use with UAV. So we think this is really going to make your life a lot easier. Some other improvements that we've made specifically with this release is we've implemented a new point collection methodology known as feature-based matching. So feature-based matching is essentially going to allow you to collect a dense set of points that are well distributed and will handle any images that are not rotated correctly. Maybe the kappa values are incorrect, and this tie point collection capability will allow you to fix some of the orientation issues, the initial orientation. Now, again, when we're working with UAV data, sometimes the positional accuracy of the scene centers can be off by 3 to 5 meters. It's more of a navigational grade GPS measurement that we get from those. And so sometimes it can be a little bit more difficult to create an initial math model to orient the images. So we can leverage this algorithm known as FBM, which has been implemented in this release of the software, to allow you to orient the images much more quickly. Another key thing is we've added the capability to tweak the accuracy settings for the different types of points in your project. So that's kind of an added benefit of this release. And one of the other key technologies specific to UAV, which Jason will be showcasing, is our new point thinning and refinement tool. So here you see on our Ortho Engine toolbar, and this is also available within Python. Basically, we have this new algorithm called point refine, and that algorithm allows you to set a target RMS. So what you can do is you can set your tie point or GCP RMS that you want to achieve, and then the software will start to remove blunders and recalculate the block bundle adjustment and keep iterating through the block until it reaches the desired RMS accuracy that you want to achieve with your data. So it's a nice tool that it reduces the manual work that's required, and it could be programmatically implemented to function the way you want it to function. Here's the same algorithm exposed within the Python environment, and so we actually have a script that we've written. Jason has written a script, and we're going to be making it available on our website. It's a full end-to-end workflow script. It's actually 2 different scripts. One is for the aero triangulation and the DM extraction. One is for ortho generation. But both of those scripts are going to be available on our support website within the coming days. And so really quickly on UAV processing, now if you remember the previous workflow that I showed where we were talking about more traditional aerial cameras, this is what UAV image processing looks like. So basically we ingest the images the same way as we would with TIFF images for UltraCam, for example. In this case, typically we're reading in JPEGs. That's how the data is captured on some of the drones, or it could be TIFF images. And those images typically have EXIF tags. So these are metadata tags that store key information that we extract. So things like the rough latitude and longitude, typically it's in WGS 84, so we can read those in decimal degrees. We also have the altitude of the drone. We can initially perform some orientation based on that. Once we do that, we collect tie points and GCPs, then we run the point refine algorithm, and then we can work our way through the exact same workflow as with aerial. We do the epipolar generation, we extract the DEM, generate the orthos, the mosaics, and do the cleanup. So I already talked about UAV processing, so the ability to collect the tie points using the feature-based matching is really what's going to allow you to derive a stronger set of tie points. And I want to emphasize that our method is a traditional photogrammetric approach. It's not structure from motion. We're not plotting our match points onto a mesh. We're actually using the actual pixels from the images based on the arrow triangulated solution that we've converged on acceptable RMS. So what we think is that this gives you a more aesthetically pleasing image combined with all of the editing tools. It really gives you something that's more professional looking. The camera calibration should be supplied in this case. So we expect you to bring camera calibration. Now that can be camera calibration that you bring in from the manufacturer, or it can be camera calibration that you derive from an external system. So Pix4D or Agisoft, sort of internal camera calibration is available, and those parameters can be actually walked over to our software, and then you can pick up from there to do the arrow triangulation and perform the full processing. We support the camera calibration file format that follows the USGS specification. So you can see here a sample camera calibration file from phase 1 industrial. We can read in the .cam files, and all the parameters will be read in. And so we support external camera calibration, as I mentioned. It could be Pix4D or camera calibration software. We actually have some camera calibration software to recommend to you if you want to perform that kind of camera calibration on your specific drone. We've been working with some of the leading researchers around camera calibration, such as Dr. Clive Fraser from the University of Melbourne in Australia, and he certainly has a piece of software that it's pretty inexpensive and quite powerful to perform camera calibration. This is just an example of external camera calibration from Pix4D that's been put into the format that we can read into our software. So with that, I'm going to pass over to Jason for the first demonstration.
Hello, everyone, and thanks for coming, for attending this webinar. As Kevin has presented, I will be showcasing all the steps for the UAV workflow in OrthoEngine. And as he mentioned, all the steps that you're going to see can be scripted into a Python workflow. So to begin, I'm actually going to just showcase the raw DJI imagery. We'll be working with these 21 scenes just captured over an urban area, a residential neighborhood. And so to start this process, I'm going to open the OrthoEngine project file and to create a new project. So I'm going to go to File, New. I'm going to set a project name. So for this, I'm going to call it UAV _ ingest. I'm going to give it a name as well. We'll call it Urban Webinar. And since we're following very similar workflow to that of our aerial processing, we can use the same math modeling method. So we'll choose aerial photography. For the camera type, we're going to keep it a digital format. For the exterior orientation, because we're going to be improving the initial aerial triangulation or the relative model with tie points, we're actually going to keep it at default and set for compute from GCPs and tie points. And then we're going to click OK. The next window for set projection, we actually don't need to set any of the parameters because the raw imagery, the JPEG files actually contain the EXIF tags, which will then be automatically read in from the OrthoEngine project file So this window will be populated. So I'm going to click cancel, and what we can see is that the error warning message says the projection information is not complete, so you can enter it in, or it will be automatically populated from the first image, which it will be. So I'm going to click OK. So the first step then, or our next step, will be to set the camera calibration. As Kevin mentioned, I've already created a camera calibration file. It's just in an XML file format, so that's easy for me to import it into our system. So I'm just going to showcase what it looks like. This is the XML file format. So all I need to do is click import, point to the camera calibration, and all the required parameters, so focal length, chip size, principal point, offset, are all populated. And then click OK. Our next step, in the Ortho Engine GUI, what we can see is there's a drop-down list of different processing steps. And depending upon your workflow, you may use some or all of those steps, depending on what deliverables you require. So for this, I'm going to choose data input. So we're going to load in the imagery. I'm going to choose the open, new, or existing images, select add imagery, point to the raw folder. I'm going to just go to view, details, and we can see all the DJI JPEG files. I'm going to select all of them, click enter, and we can easily process all those JPEG files. However, we do offer the option to convert it into PIX file format, which just is an optimum processing system for our technology. So for that, I'm going to just say yes. It's going to quickly ingest each of the 21 images, converting them to our PIX file format, so that we can then process them through the UAV workflow. So in just a few more seconds, 3, 2, 1, excellent. And 21 images were identified and 21 images were ingested. So I'm going to click OK. And in a normal traditional aerial workflow, this is where we would then import the exterior orientation file. We'd use the import EO data from a text file. However, because each of the images actually contain the XIF tags, it's automatically read. So if we actually open up the manually edit EO calibration data, we can see all the information has already been populated. We can then go to view, our project overview, and we can see that we have initial footprints for the aerial, for the UAV imagery. However, it's important to note that if we go and showcase the imagery, the kappa values are off, and the relative accuracy is quite low, and we need to improve upon this with our tie point collection technologies, because we can't actually utilize this block right now. So I'm going to close this, and I'm going to the next processing step called GCP TP collection. Here, if I had reference data sets, I could collect ground control points, but for the purposes of this, I'm just going to go to the automatically collect tie points. Here, we have a number of different tie point collection methods, but what I want to choose is the feature-based matching. Here, I could select exclusion masks, select a rejection threshold, so any tie points collected above a certain residual will be ignored or removed. And we can thin points and set a number of different parameters as well, and we then collect the tie points. Unfortunately, this process is a little time consuming for this webinar, so I've actually gone using these exact parameters, created a project file with the tie points collected. So I'm just going to keep this to the top left just so we can see the iterative improvements. So I'm going to open up the folder, AT process, and I'm going to open up the FBM collection. Wonderful. In just a few seconds, it'll be loading. There we go. So for a few things to showcase is one, the model, or the project overview. Here, we can see that there's been a significant change between the two, the ingest and the FBM. We can right-click, showcase the imagery, see that our initial, all the images have been properly rotated for alignment. We can still improve this further, but we can see there has been an improvement from the initial image. I can then go right-click on the images, show tie points or TPs. I'm going to also remove the imagery. We can see there's tie point distribution across the whole block. However, I can also go to the view, tie point distribution, and showcase the color-coded connectivity. This will showcase tie points that are multi-ray. We can even open up the tie point color coding table to see the areas that have more rays, so compared to others that have less. And this is easily seen in the center where there's a lot of images overlapping. We can go to the GCP-TP processing step and view the residual report. This displays the overall residual error for the block and the individual residual error for each of the tie points collected. Now what we're going to see is the residual error is going to be overall high, and the individual points as well are going to be quite high too, but we can improve upon that utilizing our point refinement techniques. So I'm going to close the original data set, and so we're going to keep the tie point collection or FBM tie point collection project to our left so we can then compare it. I'm going to close it and open up the point thinning and refinement tool. This one of the new technologies introduced for Banff. We can set a number of different techniques to refine our model. We can choose GCPs or tie points. For this purpose, I'll just refine the tie points. We could set a maximum residual that's allowed for the overall block bundle. So I'm going to keep it at 2, a nice default. If I want, if there's any images that are problematic, I could deactivate them if they have a minimum of 10 or whatever number I require of tie points. And once we run the tie point refinement or the point refinement tool, we'll have the residual summary of showcasing how many points have been removed and what is the overall RMS. But again, for the purposes of this webinar, I'm actually going to showcase the result. So we're going to close that. I'm going to go back to the project overview and open up the next project, which is the FBM collected refined DEM. Just going to take a few seconds. Perfect. Wonderful. I accidentally opened 2, so I'm just going to close 1. There we go. Save it. I'm then going to go to our residual report and open up the original or the FBM residual report, and we can see that the point thinning refinement tool has refined the overall block bundle to below 2 pixel residual error. So from 12 to 18 to below 2. And then if we compare the individual tie points, the points have been reduced in the residual errors. But from this, we can then utilize other technologies such as the our new software package TieImage, or our new technology TieImage, which is only available at this moment in the Python and Easy environment, which can be used to further improve this block of this relative accuracy. So I'm just going to close the FBM pre-refined method or project. We can again showcase the project overview, which has been again improved upon. And once we're satisfied with the block bundle and its accuracy, we can then go to extract our elevation models. So I'm going to go to the next step, which is the DEM from stereo. Here we have a 2-step process to generate our elevation models. The first is to create the epipolar pairs. So the system will identify optimum pairs of overlapping or stereo images, which will then be used to create epipolar DSMs, which we will then merge together and geocode into one final elevation model. So I can set the epipolar pairs, run the process, close. Then the automatic DEM extraction window will then be populated with all the pairs we just made. I can then select all the pairs to use for the DEM extraction, choose the extraction method, and as Kevin mentioned, we'll maintain the SGM method as it produces DMs with high quality. We're going to set the pixel sampling interval to 1, which will enable us to create a resolution. A DM at the 1:1 resolution, We can then create a geocoded DEM, set an output, and set the resolution to the one-to-one resolution. We can then generate the DEM and utilize our DEM editing tools to remove or fix any artifacts and filter it into a digital train model to be used for orthortification. So I'm not going to actually showcase the DEM editing tools from this DEM. I'm actually going to showcase a different one to showcase how I can edit a bridge, for instance, or an overpass. So here, again, just the pixel sampling interval, set it, put the resolution, and generate the DEM. So I'm going to close this and close this project and open our next step, which is the DEM editing. There we go. So here we have a DEM that I extracted from stereo imagery, and we can see that there's a number of artifacts underneath the bridge. I've accidentally opened it twice. Thank you. So if we generate our ortho images and our final mosaic and we do not fix this artifact, there may be problems in our output files. What we could do is we can leverage our DEM editor. I'm going to go to our layer DEM editing tool. And here we have a number of different capabilities to QA this DEM. First is the live ortho preview. This will on the fly ortho rectify all the images used to produce this DEM and showcase what they will look like based upon the DEM at the moment. But as we make changes to this DEM, the images will also update based upon the new image or the DEM pixel values. So what we could do is I'm going to move this to the left, have the preview to the right. I'm going to zoom in to the bridge, and if you noticed, as I move my cursor around on one window, it's updated on the other. So here we could see, if I look at my ortho that would be generated from this DEM or DSM, that there's going to be some artifacts underneath the bridge. I can also cycle through all the other orthos that overlap this exact area. So there's going to be artifacts unless I fix it. I've confirmed that. Sorry, excuse me. So what we could do is utilize the DEM editing operations. How we can perform the operations is first by creating a DEM editing polygon layer. From here, we can then create the DEM editing polygon. So I'm going to create two polygons, one underneath the bridge, and then the second one over the bridge. I'm just going to move this to the right, zoom out. I'm going to then create the second polygon. My apologies for that quick shift on my screen. I'm going to create another polygon just along the bridge. Great. Wonderful. And now, as I've created the polygons, we now have access to the whole list of DEM editing operations available in the DEM editor. And depending on what artifacts or fixes you're trying to make or remove, different operations will be used. For this purpose, I'm just going to use one, and that's opposite ends fill. This will take the pixel values at the ends of the polygon and interpolate them throughout the polygon. So we're going to see, I'm going to move the DEM over here. I'm going to then select the polygon, and we can see that my area has shifted. I'm going to just move this a bit more. Wonderful. I'm going to then select the opposite ends fill, blend ends only, apply with overwrite, and we can see that I've removed the pixels, the artifacts, and immediately that ortho image has also adjusted based upon the new pixel values. However, I'm going to add the next polygon, or for the bridge, And we can see that we've fixed the artifact so that when this ortho image is generated, those artifacts due to the overpass will no longer be present. So I could just zoom in again, and we can be confident that when we generate this ortho image, these artifacts won't be present, and we can make sure that these pixels are visible in our final ortho mosaic. Now, once we've extracted this and filtered and edited the DSM, which is the digital service model, into a digital terrain model, we can then utilize that for our ortho rectification. Once we've ortho rectified our images, we can then go through the whole mosaic process to create our final ortho mosaic. We have a whole range of different operations in the mosaic tool to create our final ortho mosaic. For the purposes of this webinar, I'm going to skip over the mosaic step, but talk about the post-mosaic editing. Because once we've created the final mosaic, we can then perform our QA. And if there's any areas of artifacts that we've missed in our mosaic process, we can easily fix them. Instead of having to go through Photoshop, for instance, we can actually fix the mosaic in our focus window. Or we don't have to go back to the DM, fix any DM artifacts, regenerate the orthos and regenerate the mosaic. We can just do it in the mosaic tool itself. So I'm going to close the mosaic, or the DEM. Just going to close this whole file, and I'm going to open up the Smart Geofill tool. So this tool enables us to skip using Photoshop, and enables us to not have to go back to any of the previous steps, such as the mosaic step or the DM editing step, to fix any blunders. So here's another UAV mosaic over a town, a Swiss town. And I want to bring your attention to this little bridge right here. And we can see that when I was mosaicing this, I made a mistake and I forgot to fix the bridge. So instead of having to go all the way back to the mosaic tool and re-edit my cut lines and redo all the color balancing, or even go back to the DEM in case if it's a DM related problem, I could open up the Smart Geofill tool. And this tool will load in all the overlapped images, ortho images over this mosaic. And then when I create an area of interest, it will provide me new pixels that I could paste in along with blending and color balancing options. So I don't have to do anything in the mosaic tool. So I'm going to open and point to all the ortho images used to create this mosaic. It's going to take just a few seconds. All of the images are being loaded right now as we speak. We can see the little source list of all the images here, source file list. And now I'm going to create a polygon, an area of interest over this bridge. So I'm going to go around the bridge. Wonderful. And as we go through and make the polygon, at the top right corner, we have now a number. And that's the number of ortho images that overlap these, or this area of interest, that provide us pixels that we can use to fix this artifact, this issue. So what I'm going to do is we can cycle through. As we can see, some have a little bit of overlap, some have a lot, and I can keep on cycling through. So I'm going to look at, let's say, number 17. That's good, but let's look at number 18, and that's even better. So we found proper pixels to use. However, if I were to hide the outline, there's still some color balancing issues and maybe some blending issues. So first what we could do is select the blend width, which would make a nice blending around the area of interest, just to make it more seamless. And we can select the automatically apply color balancing, which again just applies color balancing to make the whole area more seamless, so you don't have to do that back in the mosaic step. So once I'm satisfied with the results, I can then paste the pixels in. I can then remove my area of interest, and we can see that those pixels have been pasted in, and I can save this mosaic and use for additional processing or analytical tools. So I'm not going to save it, but we can just continue to use it.
Thanks, Jason. Thanks for that demo. So I'm just going to show my screen once again here. So we have another quick poll for you. Just want to make sure. So, okay, we're good. So, really quickly, whoops. So we're just curious about what's your preferred environment for processing data. Would you be happier in a desktop environment? Would you be happier with an automated Python workflow that's scripted? Maybe you prefer to use a cloud-based SaaS tool. Maybe you'd actually prefer to embed this in your offering. So possibly you're a company that just wants to offer UAV processing as a service and you're looking to OEM our capability inside your offering. That's certainly a possibility as well. We're just curious as to what people prefer. That helps guide us in terms of our development roadmap, where we want to put emphasis. And it's just useful to know in general what kind of preference you have. We have a lot of customers who collect data that we're familiar with who are in the field, and so sometimes a desktop computer is the only option because the internet connectivity is not very good. So maybe that's what's going to come out of the poll. So I'm going to just shut it down in a few more seconds here, let a few more people vote. If you did say other, let us know what that is. We'd love to hear it. Just type it in the questions box. So we're going to close that down in 3, 2, 1 and just show you the results. And you can see that a lot of people are using desktop. I don't know if that's because of our audience today or if that's a general trend. That's very interesting to see. So thanks for providing the answer to that one. So moving on, just a couple of things around DSM. So one of the key things that Jason showed is all of that error triangulation work that goes into converging a model and having a high or a low RMS and a high degree of accuracy is around the desire to create DSMs at one-to-one resolution. So we thought we would highlight just really quickly some of the conditions that will help you derive those high quality DSMs. Good camera calibration is obviously very important. Take care of all the lens distortions or aberrations contained in the lens. Being able to add surveyed GCPs with heights is obviously very useful as well. What we found is if you want to do a true ortho or a DSM ortho product, you should collect with a high amount of overlap, and the DSMs are just going to be higher quality. You get more looks at all of the different pixels, and that's going to allow you to produce a much higher quality DSM, but also ortho and mosaic. And obviously the other key thing is just have a good point distribution and a low RMS, so making that math model converge to get a very accurate model. We have some results here that we just want to highlight really quickly. This is a 1 centimeter DSM that was derived from Wingtra data. Wingtra is one of these VTOL drones. It's from Switzerland. And so that's the DSM, and this is the ortho mosaic that was derived from that data set. And if you focus on that little red box there, I'm going to zoom in at 1-to-1 resolution over that area to show you the level of detail. And you can see if I actually go into this particular vehicle here, what's kind of interesting is you can see there's a feature at the back of the car, and that's actually the trunk or the boot of the car that's up. And I'm just going to go to the next image and show you that, so you can see that it's actually open. And so that's the level of detail that you can see. You can also, you can see the side mirrors on the car as well. So, you know, having this information available for analysis is really, we think, going to be useful for many different applications. Some other examples, this is a sort of a more natural environment, like a mining area with different stockpiles collected from eBee. So this is just a kind of a nice data set. Here's what the ortho mosaic looks like, so you can see it's quite nice. And we really encourage you to download the software and give this a try yourself. You can really see the quality there that's in this data set. And so I want to turn my attention now to the next topic, which is object-based feature extraction. So what we think is also very useful with all of this is, yes, we can stitch the imagery. Yes, we can produce high quality products, similar, or we hope you think better than some of the other software that's available. But then what? So, customers, what we heard is they want to extract information from their UAV imagery, and they're looking for a way to do that in an efficient manner. So we've actually developed an object-based image analysis tool that we think works really, really nicely with UAV data in particular, because we're able to extract the DSMs at 1:1 resolution, and there's that information that's available to use in our object-based image analysis. So we have a demonstration which we're going to show. I'm going to flip back to Jason in a minute, but basically what we've done is we've used a high-resolution data set, that Wingtra data set over that Swiss village just outside of Zurich, and we've extracted the DSMs at 1:1 resolution, and we use the DSM to DTM conversion to generate a height model, which can give us information about the height of all the objects in the data set. And then we use the RGB data to do the segmentation to create the objects, and then we can use all the statistics available to us to perform more advanced analysis. In this case, we chose to focus on solar panels, which are seen here. And Jason's going to be showing you how to do this in our software, so I'm going to pass back over to him.
Thank you, Kevin. Give me just a sec to show my screen. And as Kevin mentioned, I'm going to just showcase the object-based feature extraction of solar panels. So as we saw in the PowerPoint, I have a nice little mosaic over the Wingtra urban area. And I have a number of different solar panels on different houses or buildings. So we can just zoom across and see. And from the data set, I created as Kevin mentioned, a normalized height model, and utilized a texture measurement to help with segmentation, and a slope measurement, which we could see here, to just help discern between the building and the actual solar panel. So here we have our red, green, and blue, the texture, the slope, and the height model. And just to again show, we have the RGB, the slope, and the height model. Now, to give a brief overview of what is Object Analyst and with the feature extraction, we can find it under the Analysis tab called Object Analyst. And in this window, we have two parts. We have the operation drop-down list, and again, very similar to the Ortho Engine list, sequential steps, depending upon what you're trying to extract and your methodology, you may use all or just a few of those operations, and the processing canvas, which documents all of the steps and the operations that you run in the project, which can enable you to easily go back, rerun different operations based upon the results, and just keep everything documented. And this is quite useful, especially if you want to run batch processing as well, which we've done a whole other webinar on last week. So the first operation is the segmentation, and this will segment the imagery based upon the pixel values and the channels we have derived. So just to showcase my segmentation, if I select Edit, I segmented it based upon the red, green, and blue, the texture measurement, and the height model, just to help discern between what is a building, shadow, grass, vegetation, just to create the segmentation. From that, I then ran the two attribute calculations. The first with the RGB, and I had a number of different statistical measurements. So we had min, max, mean, standard deviation, geometrical attributes, and vegetation indices, which is a new feature as well. If we had NDVI, we could automatically extract all the vegetation indices we see here, but because I had RGB, only GRVI and GI. After that, I extracted a texture measurement as well, just for the mean. I then ran a second attribute calculation focused upon the texture, the height, and the slope, and that was just for statistical measurements. Once I extracted the attributes, I could open up. I don't want to showcase that yet. I can open the attribute model, or the attribute manager, and we can see that all the information has been populated. And this is quite important because this will be used for the supervised classification that I ran. So once I ran the attribute calculation, I then collected training sites, and that is the training site editor operation. Here, I collected a wide array of training sites for the different types of surfaces and features we have available. So first, to zoom in, we were able to run the segmentation, and that's what the red area is. But we can see if we zoom in, the segmentation was successful to even identify the individual solar panels. For the training sites, I extracted buildings, the impermeable surfaces such as asphalt and pavement, permeable surfaces, so grass, as we see on the left, solar panels, the actual solar panels over here, trees, and water. So once I collected a wide array of training sites, and I wanted to make sure that my training sites cover the different types of land covers and land classes, I can then run the supervised classification. This, go to the edit, utilized all the attributes that I collected in both those attribute calculation techniques or operations. I then set the training field that I collected the training sites under and ran the classification. And if I wanted to, if I had a whole batch of imagery to process, I can then save this training model to use for batch processing. So the result of this is every single segment has been classified based upon the model we used. So just in a few seconds, everything's going to be highlighted. Wonderful. So again, green, the pinks, the yellows, all related to the different classes. So we can even zoom in. There has been some misclassification. If we zoom in over here, for instance, some of the shadow from the building is actually being considered water. And that's mainly due to the fact we only had RGB instead of the NIR because it probably confused shadow with water, unfortunately. But because our purposes were for just the solar panels, it's okay. I can then utilize rule-based classification. So I generated rules from the attributes I extracted to reclassify any misclassified segments. So we can see that along the building, for instance, some segments were classified as solar panel, even though they should not be. So once I ran the rule-based classification and I refined my results, I was then able to successfully extract all the solar panels across these building features. Let's zoom in. Now, I was focused mainly upon the solar panels. However, this doesn't mean I wasn't able to extract, or a user should not think about extracting other types of features as well. So we could see I extracted all the impermeable surfaces, so all the roads. I was able to identify the rough building footprints, the permeable surfaces and the trees, and all this can then be used for further analytics.
Great, thanks, Jason. So we're just coming up on 3 o'clock. It's been a pretty busy webinar. We're showing you a lot of things today. I'm not used to this. We've got another poll. So just real quickly before we start to wrap up here, we have been getting a lot of questions. We've been trying to stay on top of answering them, so we might not have a lot of time for Q&A. So hopefully we've been answering them as we're going. But we currently have a question up on the screen. If you can improve one thing in your UAV workflow, what would it be? So we're kind of curious to know what that would be. Would it be related to reduce processing and editing time, so make things go faster? Would it be to implement a scalable UAV processing solution? Are you more interested in quality of results, automatically extract features from UAV imagery, or other? So we're just curious to know what that would be. A lot of you are weighing in right now. I'm going to leave it open for just a few more moments. We're close to wrapping up. We're just going to point you to some resources that you can go to. We've had a number of good questions through the session. It's been a very engaged audience. Great to see. Thank you so much. So I'm going to leave it open for just a few more moments. So 3, 2, 1. If you didn't get a chance to vote, sorry about that. But I'll share the results. So looks like improved quality of results, automatically extract features, followed by reduce processing and editing time. So that's pretty interesting results. Thanks for that. So I'm going to hide that and go back to my presentation. So just to wrap up, I guess, so for the resources, we do have our customer support team ready and available to support you if you're an existing customer and you're not currently using our UAV processing tool because it just came out, or a UAV processing workflow that's part of Geomatica. You can definitely reach out to them, and they will point you in the right direction. If you're used to using our aerial processing package, everything should be very familiar because it's exactly the same in terms of how it works. We have a Python script available. Jason wrote a Python script in preparation for this webinar that will take you from JPEG files all the way through to ortho Mosaic. So we'll be pointing you to that script. It'll be up on our support.pci or support.pcigeomatics.com destination site, where we have a number of resources, including tutorials and lots of other material. We also have a Udemy course that focuses on aerial data processing. It's actually the data set that Jason was showing, one of the data sets that Jason was showing, which is an UltraCam data set over the city of Hamilton, Ontario. So you can get to learn our software using that resource. It's a free course. You just have to register, and it's little videos and sample data, and everything is all packaged and ready to go. We have a considerable library of YouTube videos, over 130 videos at last count. They're organized into playlists on different topics, so I encourage you to check those out. And last but not least, I just want to ask one last poll, which relates to the availability of Jason to support you, which is so I'll just talk about it while I'm showing it. So we have Jason and we have other people like Jason available to help you evaluate Geomatica. And so basically, as you saw, Jason knows how to use our software. He understands what kind of you're trying to achieve as a customer. He can actually pick up some of your data. We have a secure way for you to transfer data to us using a share file system, and run your data, and then show you the results of that. So if you're new to PCI and you don't want to invest the time to learn the interface and you'd rather just have someone process the data for you and show the results, and then have a quick meeting with you to kind of showcase whether this is a fit for you, then someone like Jason is available to do that. So anyway, I'll leave it at that. Thank you so much for answering that. And I'm going to move to the last slide, which is our Q&A, and we're exactly at 3 o'clock. It's been 1 hour exactly. I think we packed in a lot of information. I'm going to keep an eye out on the questions panel to see if there's any last minute questions. We've been trying to answer them as we've been going, and we've been broadcasting the answers to everyone that's attending. So let's see. So we have a question about, is it difficult to do proper camera calibration when low cost cameras are mounted on the drone, such as GoPro or Canon DSLR? We don't have a ton of experience with that. What I can say is that we do have a recommendation, which is to use Dr. Clive Fraser's software. It's known as, I believe it's called Photometrics. I'm gonna throw his card up on the screen here. I don't know if you can see that or not. But I put the link in the questions panel. Just ran into this gentleman. I met him in person when I was at a conference in Australia, and he's extremely knowledgeable on camera calibration, has developed a software kit that does camera calibration, and it only costs about $950 US, and it provides you the option to calibrate your camera on your drone before you fly, or it can perform the camera calibration using the actual pictures themselves. Now, we are working PCI on camera calibration technology ourselves, and we hope to make that available soon. But in the meantime, you can definitely use Dr. Fraser's software to do that, or do some other estimates of the camera calibration using other techniques from other technologies such as Pix4D or Agisoft. There is camera self-calibration built in, and you can take that information over to our software and perform the full processing there. We have an interesting question that just popped in. I'm not sure it's related to UAV, but it's aerial photos. It relates to aerial photos from 1975. So how can I build an ortho image from 2 or more images from 1975? So we actually have a full capability known as historical air photo processing, or HAP, and that's a dedicated workflow that will allow you to take old historical images and process them to create orthomosaics. It's not today's topic, but it's definitely something that is available for you to check out. And I can pull up a gallery on that, or I can point you in the right direction. I'll send you a link here. I'm just going to write PCI Geomatics.com/. If you just go there, I'm just sending the link through the questions. You can definitely check out some galleries where we've processed historical imagery and made it available. We have some questions about licensing options. So I encourage you to get in touch with sales. I'm not trying to dodge the question, but I don't want to broadcast the price of everything, because we actually take a lot of care to price our software in a modular way so that you only buy what you need to use. So we have 2 versions of our software. We have Geomatica Core and Geomatica Prime. The main difference between those 2 environments is one allows you to work more manually and it's a little bit less expensive. One allows you to leverage automation like Python. And then there's modules that are related to aerial data processing, modules related to satellite data processing, modules for DM extraction, and so on. So it's a modular software, and we are certainly competitive, we believe, with the other packages. However, what we do is we are positioning a software platform that not only does the stitching, which is primarily what Pix4D and Agisoft and other software like that does, but we allow you to do so much more, because we are a remote sensing company. First and foremost, we are image analysts, and we have that in mind, and hopefully that came across today. But I encourage you to get in touch with us if you have specific questions about anything related to our software. My email is jones@PCI Geomatics. Jason's email is flat@PCI Geomatics. We have a lot of ways to get in touch with us. Thanks for being here today. I think it's been a great session. I want to thank Jason for giving the live demonstrations, and thank you most of all, attendees, for spending the last hour with us. Have a great day, everyone. Bye-bye.